infinite number of things, such as like, how can you even really do that? Doesn't that take an infinite amount of time? You know, et cetera, et cetera, et cetera. So if you are spooked out by this, good. And this is what we're going to be talking about for the next 20 minutes. Adding up an infinite number of terms. Now, because this is so philosophically dangerous, we need to have a conversation about math. That you may have already reached this level of philosophical sophistication, but perhaps not. Okay, and what we need to talk about is the distinction between sort of symbols and their meaning. All right, for example, I'm going to write something on the board right now. Is everyone sitting down? And okay, make sure your shoelaces are tied and whatever. It's going to be pretty scary. Yeah. Okay, so 4 divided by, do you dare me?
Do it.
0.
Oh my god.
Okay. Yeah. Did you get a little shock there? Did you get some heebie-jeebies? Whatever they. Okay, this is, please someone comment on 4 divided by 0. Hannah.
It's not possible.
It's not possible. You cannot divide by 0. That is true. There is no such thing as division by 0. Why? Because division is really just multiplication by the reciprocal, and 1 over 0 is undefined. Why is 1 over 0 undefined? Because 1 over 0 just means the multiplicative inverse of 0, and 0 has no multiplicative inverse because you cannot multiply 0 by something and get 1. Because 0 times anything is 0. It all really does make sense. So as 0 has no multiplicative inverse, 1 over 0 is undefined, thus you can't divide by 0. So this is just impossible. So this is just undefined. Nonetheless, I wrote it on the board just fine. And nothing happened. It's not like some house down the street just exploded or something from the force of writing this, okay? And in fact, this is a little bit mysterious because I know what 4 is, I know what 0 is, I know what division is, so it would seem that these symbols would all be able to go together, but they just can't. Okay, the moral of the story is, just like Michael Tang's life, the moral of the story is, just because you write something down on your paper does not mean that it is a thing. This is nothingness. This is simply undefined. This is basically like garbage. This is a not ending the Michael Tang parenthesis. This is just a meaningless combination of symbols. Okay, it would be as if I tried to. Okay, so consider the following sentence. The boy into. That's it. That's the end of the sentence. Okay? We know what the is, we know what boy is, we know what into means, but that combination of 3 words is just meaningless. It just doesn't say anything, right? That's not a sentence. I can't say whether it's true or false or anything. Similarly, 4 divided by 0 is just nothing. Is everyone okay with that? This actually comes up all the time. What if I write like tan of pi over 2? Now, that might not evoke such a visceral response. Like this time Carl didn't fall off his seat. But what is tan of pi over 2? Doesn't exist. It is just undefined. It is nothing. So this combination of symbols is meaningless. It does not refer to anything. And this happens all the time. Just this happens a lot in geometry. Just because you draw something doesn't mean that it is really a thing. For example, here's a beautiful triangle. Wonderful right triangle. Didn't I draw it and everything? Yeah, well, you can draw all kinds of crap. It doesn't mean that it's actually a thing, right? So this is meaningless, and this is meaningless. Okay, you must be on guard all the time for this, because when it comes to adding up an infinite number of things, there's a lot of things that are meaningless. Such as, consider 2 plus 2 plus 2 plus ... What is this? It's like infinity, whatever that is. That's also just like not really a thing, right? And it's definitely not a number. 2 plus 2 plus 2 plus 2 plus, I claim is nothing. Can I get a proof? Prove to me that this could not possibly be a thing.
I mean, you can't add numbers and punctuations.
Whoa. Argument from punctuation. No, something better. Catherine.
If you said 2 plus 2 plus 2x, then x is equal to 2 plus x.
Yeah.
0.
Genius. Catherine says, pause for a second. Catherine says, okay, let's just suppose for a second that it is a thing. Let's suppose for a second that I can add up 2 plus 2 plus 2 plus 2 plus and get a number. Okay, Catherine, continue.
Then x plus 2 is equal to x.
Ha. Then she says, why don't we group things like so? And thus, does everyone see what's going on here? You want to keep talking, Catherine?
2 plus x equals x, which means 2 equals 0.
And that is not true. Okay? So, on the assumption that 2 plus 2 plus 2 plus 2 is a thing, we proved that 2 equals 0, which is just false. So, 2 plus 2 plus 2 plus can't be a thing. Okay, so it appears that we have to constantly, when adding up an infinite number of terms, be worried that what we are writing down is total nonsense. But, however, other times, it appears that what we are writing down is not nonsense. For example, take 1/2 plus 1/4 plus 1/8 plus 1/16, etc. What is that? That's good. Can I get something more detailed than good? Have you seen anything for us? This is like middle school type stuff. What is this? Everyone. Yeah, this is 1. Why? Randall, why?
Equals, if you make it equal to x, and then you make it like, then you take 2x, you have 1 plus 1/2 plus a 4th, and then you subtract 2x and x, and you get 1x equals 1.
Wait, I didn't follow that at all. Wait, hold on. I haven't even heard of this before. He said call this x, then do what?
Then 2x.
Like multiply everything by 2?
Yeah.
Okay, so then he says multiply this up. Oh, this is so cool. Maybe that's going to do hard, but maybe not. Plus dot dot equals 2x.
Then you like subtract x from 2x.
But then that's just x.
Yeah.
So 1 plus x equals 2x. So x equals 1. Nice. For that, you can get a signed autograph of someone a little better than Garrett Temple. How about, I don't know, that deserves an Otto Porter. Except I also spilled coffee all over that one. Catherine, you can have Martell Webster. Very famous, not NBA player. All right, good. So, good. Yeah. And by the way, does anyone have like a more informal argument that this is 1? I mean, yeah.
So you have a box, and then keep on adding in like 1/2 of what's left.
Yeah, this is like how they do it in middle school, I think, right? Take a box of size, take a square of size like 1. If I add up 1/2 of it, then that's like that. And then 1/4 of it is like that. And then 1/8 of it is like that. And then 1/16, and each time we're adding 1/2 of what remains. And it certainly does appear that that's 1. I don't know whichever of these you find more convincing. Okay, so, and in fact, now is a good time to talk about this thing called Zenos Paradox. So, have you guys heard of this before? Middle school math classic. Zenos Paradox. Who was Zeno? A mysterious and cantankerous ancient Greek philosopher who was engaged in a philosophical dispute in which he was trying to show that all change was impossible, and that in fact the world, that all change was just an illusion, and the world was just perfectly still and nothing was moving or doing anything at all. And in order to convince people that this was true, he wanted to prove to them that actually certain obvious things, like someone running was in fact just an illusion. And here was his argument. He says, okay, he has about 10 paradoxes, all slightly different from each other, all very interesting. One of them was called the paradox of Achilles. It goes like this. Suppose Achilles, ancient Greek hero, was running a race. Well, says Zeno, Achilles can never finish the race. Because if he starts at the beginning, in order to get to the end of the race, he must first reach the halfway point. Having reached the halfway point, he still has half a race to go. Well, he can never cover that distance. Because in order to cover that distance, he must first cover half the distance, thus arriving at the 3/4 point. And having arrived at the 3/4 point, he still has a quarter of the race to go. And he cannot possibly cover that quarter of a race, because in order to cover it, he must first reach the halfway point of what remains. And then he's now at the 7/8 point, and he still has distance to go. And he can never cross that distance, because in order to cross that distance, he must first cross half that distance. And so says Zeno, he can never finish the race, because it is not possible to add up an infinite number of finite quantities and get something finite.
Wrong.
Is it wrong, Reynolds?
We just did it.
Yeah, Reynolds says, so this was considered very convincing at the time, and now Reynolds says, no, I reject exactly the moment that Reynolds turned out wrong. That's what mathematicians of the past couple hundred years have also agreed on. That last part was just wrong. It appears that we can add up an infinite number of things and get something finite. Sometimes. Other times not. Okay, so this is like a big problem. Does everyone feel this? Sometimes we can add up an infinite number of things and get something finite, other times not. Alright, this was not resolved until the 19th century. And in the 19th century, that same generation of mathematicians who also came up with these really, really fancy definitions of what it means for a sequence to have a limit, also tried to tackle this question of when precisely is it possible to add up an infinite number of terms? And here is what they said. Okay, so we'll go back to this example. So take 1/2 plus 1/4 plus 1/8, etc. And here's what we can do. Add up the first 1 terms. Call that S sub 1. What's that? 1/2. Add up the first 2 terms. That's 3/4. Add up the first 3 terms. 7/8. And in general, what we are going to call these things are partial sums. They're called partial sums because they are part of the entire sum. Okay, so it's like the sum so far. And now, what these guys from the 19th century said is, let's construct a sequence of partial sums. Make a sequence whose terms are the sum of the first 1 terms, the sum of the first 2 terms, the sum of the first 3 terms, all the way up to the sum of the first n terms and beyond. In other words, consider what happens to the partial sums as you go out farther and farther and farther. And by the way, can someone conjecture a formula for the sum of the first n terms of this particular thing? Carl?
Would it be S(n) equals n over n plus 1?
I don't think so.
No, I'm sorry. N.
Justin?
2 to the n minus 1 over 2 to the.
Yeah, Justin's like, dude, the bottom keeps growing as powers of 2, and the top is always like 1 less than that. Yeah? So yeah. Which could also be written as 1 minus 1 over 2 to the n. And now, says the people in the 19th century, consider the limit of that sequence. In other words, take the limit as n goes to infinity of the sequence determined by the sum so far. And a certain infinite sum will exist if I keep going out farther and farther and farther and farther in the sequence whose definition is the sum so far. If that sequence has a limit, then this exists. So what is the limit as n goes to infinity of S of n? Well, that would be the limit as n goes to infinity of the expression 1 minus 1 over 2 to the n. And what is that? that is 1. And so we say that this is 1. Follow? Okay, now, in general, then here is the idea. If I have a certain series, A1 plus A2 plus A3, and on forever, what I do is I take the partial sums. So S sub 1 is the first term. S sub 2 is the first term plus the second term. S sub 3 is, et cetera, et cetera, et cetera. And now what we do is we construct the sequence of partial sums. The sequence of partial sums. And it is a sequence, each of whose terms is the sum so far. And we go out to the nth term and beyond. And then we look at the limit of that sequence. And what we say is, if the limit as n goes to infinity of the nth partial sum, if that limit exists and is a number L, then we say the series converges. And we say that it converges to L. So this is a new vocab word, converges. A series converges if it basically exists. If it goes to a particular number. And we define that as the limit of this sequence, that this sequence has a limit. If, on the other hand, the limit as n goes to infinity of S of n does not exist, then we say the series diverges. Diverges. Okay. So a infinite series either converges or diverges. If it diverges, then it just means it just keeps doing something crazy and thus it's garbage. If it converges, then the number that it converges to, we think of that as being the value of the series. How do you guys feel about this? Just presenting to this solution. Okay. Should we do one quick example? Let's do the example that started this off. It's like 1/3, 1/3 plus 1/9 plus 1/27, etc. Let's figure out whether this series converges or diverges, and if it converges, let's figure out what it converges to. Okay, how do we do this? We start constructing the sequence of partial sums. The sum of the first one term is 1/3. The sum of the first two terms is a third plus a ninth, which is like 4/9? Yeah. Sum of the first three terms is that plus 1/27, so I guess that's like 13/27. So you guys following me-ish?
Yeah.
Okay, so now what I need to do is I need to construct the sequence of partial sums, S1, S2, S3, on and on to S sub n and beyond. Okay, now I have two options. I could try to guess a pattern, or does anyone know some kind of way in which we can figure out the formula for the sum of the first n terms of this series? Someone say something smart. Yeah?
So it's subtract 2 and then over 2. So, or subtract 1 over 2. So the bottom is...
Wait, say a word that makes people recognize that this is something we should be able to do.
3 to the n.
Yeah, what kind of a series is this? It's geometric. Yeah, this is a so-called geometric series. So these terms are growing geometrically. So we just have a formula for the sum of the first n terms of a geometric series, right? This is the whole magical cows thing from earlier last week or this week or whatever, right? The sum of the first n terms is just in general a times 1 minus r to the n over 1 minus r. That's like a thing that we already know. And as this particular series just is geometric, then you're just going to use that formula, right? Basically?
Yeah.
Is that what you were doing?
I was like, well, I just got it without it, but it is the same thing.
Okay, so what is this going to be? Is everyone kind of with me? I'm going fast, but I think it's okay. The first term is 1/3, and then this is 1 minus, what's r?
3.
1/3? R is 1/3, right? We're multiplying by 1/3 every time? to the n over 1 minus 1/3. What's that? That's 2/3 down there, So that's 1/3 over 1 minus 1/3 to the n over 2/3. So I guess I can cancel the 3's. So really the sum of the first n terms is like 1/2 times 1 minus 1/3 to the n. You guys following this? It's not so hard. And then if I'll just do one more thing, I'll just multiply through the 1/2. So it's really like 1/2 minus 1/2 times 1/3 to the n. So that is the formula for the sum of the first n terms. And what I need to now do to see if the sequence converges or diverges is take the limit as n goes to infinity of that s of n. And if I do that, I'm essentially taking the limit as n goes to infinity of the expression 1/2 minus 1/2 times 1/3 to the n. And what do I get? Number one, we just did a whole bunch of limits. Answer? 1/2. So since the limit of this sequence is 1/2, what we're saying is that when you keep adding more and more and more and more and more terms, you're essentially just basically getting 1/2. Follow? Okay, so the end conclusion is that this just equals 1/2. And we say the series converges to 1/2. That's what we say. All right, how are you feeling about this? Say good. All right, we have 4 minutes to do something that takes 10 minutes. Are you ready?
No.
Good. All right, what we're going to do is just the same thing over again, but we're going to do it like in general. So I would like to know, when does a geometric series converge and when does a geometric series diverge? So if S is A plus AR squared plus AR cubed, etc., on forever, the question is, when does this converge? Can someone give me some intuition on this matter? Yeah, Nick.
When the rate is less than 1.
Yes. Nick just kind of generally gets the gist of it, which is he says, if R is like a chill number, like say 1/2, that is going to be good. Why is that going to be good? Because if you keep multiplying things by 1/2, they're getting smaller and smaller and smaller, and I think that's going to be okay. I'm not sure it's going to be okay, but I think it's going to be okay. What's definitely not going to be okay? If R is like 3. If R is like 3, then does everyone see how each one of these terms is just getting bigger and bigger and bigger and bigger? This is just exploding out of control. There's no way this is going to converge. Does everyone feel that? Okay, now all we need to do is just sort of prove that that is indeed true. Okay, so what do? We construct the sequence of partial sums. S1, S2, S3, all the way on to S sub n and beyond. Well, fortunately, we have a formula for the sum of the first n terms of a geometric series. It is A times 1 minus r to the n over 1 minus r. So all we have to do is to take the limit as n goes to infinity of A times 1 minus r to the n over 1 minus r and see if that limit exists or not. You guys kind of with me, even though I'm going fast? Okay. Well, what Nick is sort of saying is it's going to depend on what r is, right? So what we have to do is we have to do a bunch of different cases. So first let's do the happy case. The happy case is when r is small, and specifically r is between -1 and 1. So if r is small, between -1 and 1, then what we're going to do is we're going to take the limit as n goes to infinity of A times 1 minus r to the n over 1 minus r. And what do we get if r is a small number, like 2/3? What happens if you multiply 2/3 by 2/3 by 2/3 by 2/3 by 2/3 by 2/3 forever?
This goes to 0.
So what's the answer to this limit? A over 1 minus r. Conclusion, the series converges. The series converges. And it converges to A over 1 minus R. Okay, that's matching with our intuition that if R is a small number, less than 1, then this should work out. Okay, an even stronger intuition is that if R is not, if R is bigger than 1, it should not work out. So now let's consider that case, where the size of R is bigger than 1. Well, if R is really big, then again, we need to see what happens to the partial sums. So we're going to take the sequence of partial sums and take the limit of it and see what happens. Well now, what happens if R is a number like 3? This just gets bigger and bigger and bigger and bigger and just grows out of control, right? So there's just no way that this limit exists. I could probably show more work and stuff like that, but does everyone see that? And in fact, there's two different kind of ways. If R is like 3, then this expression is going to like infinity. If R is negative 3, then it's going to like jump, right? You're going to get like 3, negative 9, 27, negative 81, etc. Okay, wait, 2 more cases. 30 seconds each. What about the case where R equals 1? Don't worry about Quadrano, it'll be okay. What if R equals 1? If R equals 1, then this formula is kind of like useless, right? So if R equals 1, well, what is our series if R equals 1? The series is really just A plus A plus A plus A forever. And what do we know about that? This diverges. So diverges, so the series diverges if R equals 1. We also saw that the series diverges if the size of R is bigger than 1. Okay, last case. What if R is negative 1? This is actually the most interesting case of all. If R is negative 1, then what does my series actually look like? It's like A minus A plus A minus A, etc. What is that doing? Let's look at the partial sums. What's the sum of the first term? We're going to be done in 20 seconds. What's the sum of the first term? A. What's the sum of the first 2 terms? 0. What's the sum of the first 3 terms? A. The sum of the first 4 terms? 0. Does this sequence have a limit? No. This sequence has no limit, so the series diverges. Okay, that's it. Thank you. Sorry for holding you over.
No, I don't want to go to English.
Okay, hit it off.